Okay. Well, thank you very much. It's a great pleasure being here. I've had a wonderful time in Italy, and I'd like to thank Sandra and others here who have really been very kind to me, collected me each morning, dropped me home in the evening. That I can understand more. Then get rid of me. Well, I'd like to tell you of some recent work that I've done with some Chinese colleagues in the north of China at Westlake on the influence of freezing a salty water and how that takes place. And that's, of course, important in a lot of ways, and I'll explain you some of the examples, but one that is in some sense the biggest in my mind is the effect of climate change, where no matter what the President of the United States says, it's causing an enormous amount of trouble and could cause even worse trouble. And the ice in both the Arctic and the Antarctic is melting in the relative summer, and then part of it, much of it, refreezes again, and so we want to know what's going on. Now, actually, this first slide I prepared because I was asked by a different group in China, in fact in Peking, whether I could give a talk at a big international conference on nanotechnology. And I said to them that nanotechnology was not quite my specialty, but the chairman said, oh, but you could talk about brine freezing. So I said, okay, I'll do that. And so I started with this slide, which shows you how things can get bigger and bigger from a scale of 1 basically to 100 million. And at the small scale, it's the question of the water molecule, which we all know about and know how it is shaped and everything, but not one of us has ever seen just one water molecule, but it is enormously small. And then there are glucose, which we eat, antibody, and virus. It gets bigger and bigger. There's a cancer cell, that's even more. Then there's what's written here as a period. And let me say this is the American definition of period, what I would call a full stop. Is so much larger, as you see, 1 million times larger than a glucose molecule. And I couldn't resist putting a tennis ball here because I'm a keen tennis player, and that's something like 100 times larger than a full stop. But I'm going to tell you about relatively small aspects. But I thought I would start, well, both today and at this meeting on nanotechnology by talking about not only ice, which I was going to talk about, but the biggest ice there is in the world, just to show them that they're dealing with little things. And I thought you might even be interested that the biggest iceberg on Earth weighs 1 trillion tons and is floating freely on the open sea. It no doubt broke away. This is now near South Georgia, and it broke away from a big ice pack. It's got an area, as you see here, of 1,500 square miles. It's got a volume of 263 cubic miles. It's 4 times the size of New York City and about 10 to the 8th heavier than the Eiffel Tower. So it really is an enormous business. But associated with the formation of this gigantic iceberg are little small brine veins, because the relatively pure ice froze from salty water. and it couldn't be a perfect ice crystal. It can't be, it isn't, and it has these relatively small veins which capture the salt from the ocean from which it freezes. Now, an important aspect is going to be how an ice-water system varies its density as a function of temperature, and of course this would also be true when I add some salt. Sorry, this is just for fresh water. And what I'd like to point out, as you all know, the maximum density of water occurs at 4 degrees centigrade, and the ice that's formed is a rather smaller density. As you know, when you put ice in your drink, it floats to the top because it's less dense. But 4 degrees is the maximum density, and then it decreases. Now, when you add salt, well, what we've been talking about, just pure water, there's no salt, and it will form ice below 0 degrees, but above that it's just water. But now, as you add salt, the temperature at which a solid will begin to form goes down. As you see, this ice line goes down to what's called the eutectic point, and at that salt concentration it then goes up again. So you can have above this sort of triangular shaped line, you can have just liquid water with some salt in it, but below that line you always have a mixture of ice and salt. Now, an important aspect which I'm going to mention a little bit is so-called double diffusive convection, which in the 1970s and 80s was a much thought about and talked about problem amongst oceanographers, but now, for reasons that I don't understand, though it still goes on in the ocean, and it's just as important, it's not much discussed at all. And that's called double diffusion, or sometimes it's laughed at and called double confusion, but it isn't. It's absolutely understandable, or I hope to make it understandable. And it occurs when there are two components with different rates of diffusion. So there's the temperature that diffuses at one rate, and the salt that diffuses at something like 100 times slower rate. But you can get the same sort of things with different molecules, different solutions other than water, where they're either larger or less. And there are two different situations. The first situation is where it's hot and salty on top and cold and fresh on the bottom, as you see by the red line, the hot, and the blue line is the density, in that it's definitely more dense in the lower layer. It has to be, otherwise they would separate. But even though the lower layer is more dense, there's a transfer between the upper layer and the lower layer because of the different diffusion coefficients. Because if a bit of the upper layer, which is hot and salty, goes down, it gets rid of its heat much more rapidly than it gets rid of its salt excess. And if it still keeps its salt excess, then it's heavier, and it forms these salt fingers, as they're called, because it's a way of taking the salinity from the upper layer to the lower layer. Now you can turn it upside down and have hot salty below, cold fresh, and then what happens is that slowly by diffusion through the interface the heat goes up. It also takes a little bit of salt, but not very much. And now, one of the things that I find fascinating about this subject, on which I've written a number of papers and this general review with Stuart Turner, is that I once was invited to a mainly chemical meeting down in London, and a professor of one of the big universities, and a quite well-known man apparently, he gave a talk. And at the end of it, I said, would you mind, during the Q&A, would you mind if I summarise what you've just said? And he said, no, if that's helped you. So I said, yeah, it would. So I gave a 4 or 5 line summary, and he said, that's absolutely right. And I said, no, it's absolutely wrong. He said, no. What you've said was a good description of what I've said. And I said, yeah, but it's absolutely wrong, let me tell you, because he just hadn't known about double diffusive convection. Luckily for me, he was a nice, friendly guy, and he didn't get annoyed with me. He listened to what I had to say, and he said, you know, we chemists have always known that a number of our experiments just give what we think are ridiculous results. And I said, yeah, that's because you haven't taken this double diffusion in mind. But it is very important. It'll come up. Whenever there are 2 components, it can happen. Now, what we've done, and I'll concentrate mainly on the experiments, but I'll tell you a little bit about the theory, is set up some equipment where one bit, either the top or the bottom, was kept at 0 degrees, and the other extreme was kept at -9 degrees, so that was the cold end. And what you can see is either 1 or 2 can be kept either hot or cold, and then there is a brine solution, which is 5, through which the heat is transferred, and that's because it's -9 degrees. The brine is going to get cold and it's going to form ice, but not perfect pure ice. It's going to have these little brine pockets, which are important, how much brine is there. And then we have an X-ray source that shines through the 1 centimetre high experimental equipment, and then goes on to the detector so that we know what we've seen. And this is important in investigating the structure. And what we're going to see is that the first section happens really very quickly. It comes to a state really very quickly, and the convection and the thermal transfer really takes quite a bit longer time. Well, now this has lots of applications. I've talked almost only about sea ice formation so far, but there's also lots of situations where in industry they want to get rid of the salt, and they want to see how they can form material that has not much salt in it. It's also important in food processing. Either you want to have salt in some cases because it makes it taste better, or you don't want to have salt because that's thought too much salt is not good for you. So the food processors are wanting to know about that. And then there's what's called biological cryopreservation, which I suspect not many of you will know, so the next slide will tell you what it's about. And it's a relatively new idea, it's a method of freezing living cells, tissues and organs to extremely low temperatures so that they survive and don't change. Normally they use liquid nitrogen to do that, but that's just, I think, partly because it was done before, so it's done again. And the idea is to preserve these for future use. And as you may know, it's, especially in the last year or so, there'd been quite a debate about whether you could freeze people while they're still happy and alive and then unfreeze them in 5,000 years or something like that. Now, no one, I think, has thought carefully about how terrified one would be if one woke up 5,000 years from now. Life would be totally different, and language, everything may be different. Now, whether it can really happen, we don't yet know, but it is an important aspect that's being thought about. And the important thing is that it stops metabolic activity, it stops you aging, and in some sense that's good, but you can't live a life and not age, or at the moment you can't. And the idea in part is to reduce the ice crystal formation, but just to keep everything cold and cool and delay the evolution. So that's been used in a number of situations experimentally, but it's still very much research, but much talked about. And like always with these new ideas, some people think it'll be wonderful, and some people think there isn't much to it. And as I often say, a very useful, in my opinion, analogy is when the first car or cars, a small number, were invented. Some people thought it would be terrific, and it would really do things. Nobody, I think, when the first cars were introduced, imagined that there would be traffic like there is here. And as much as I've been told a number of times and seen how much traffic there is in Parma, and I presume in Italy, nothing compared to China or India, where it's much, much worse. So here was what seemed an impossible idea, highly developed, and this may be true here also. Now, this is a snapshot, and I'll show you a better snapshot of our experiment, better in the sense that I'll divide it into two parts. But what you see, these are vertical and horizontal shots at something like 8 millimeters, and remember it's 10 millimeters, the total height, and 5 millimeters, and then at 5 and 2 millimeters. And the difference between freezing and freezing from the top and freezing from the bottom. And what you see here that's dark is porous ice. In other words, there's lots of ice crystals, but they're not forming a solid at all. And what you see in bright colour is the brine. This is where there's still quite a bit of solution, and it's white in this. And here you see the difference between solidifying from above and below. When you get downward freezing, you tend to get columns. And when you do upward freezing, you tend to get skirts, as we'll see. They're really rather different. Here you see it better because I've taken a smaller section, and the left is freezing the brine solution from above, and the right is freezing the brine solution from below. and both have some interesting applications. And first you see in the first 6 square figures that there's a lot of structure, really a lot of structure that gradually changes, but it takes some time in our experiment, a day or two at least. We've ran them, and as I say, you can see the structure of the skirts and the columns, and I'll talk some more about that in a moment. This is now much later on, where you see on the bottom of the left 3 that the fluid, the brine, there's quite a bit of it now because it's left behind the solidification of the solidish ice, and of course the other way around, if you call it in the other way around. But you see there's still a lot of structure. You can see that both in the horizontal plane and in the vertical plane. And that structure is what we'd like to understand. And now what is interesting is, now first I'll apologize in that the temperature scale goes from 0 to -10 to the right, whereas I've said to my co-authors it should go from -10 to 0. And while they take account of most of my other comments, that one they don't want to do, I've not understood. So it's a little bit difficult to understand. But we've now got a situation where there's a downward freezing, so it's cold at the top, and when the experiment starts, the temperature suddenly turned on, and it goes to a uniform gradient, which is basically S1. And then quite quickly, in seconds, it goes to S2. So the temperature, which can diffuse rapidly, does do that, and it's influenced by what goes on at the top, and it looks like S2, a more or less uniform region, and then a gradient. Then you get S3 and S4, but they take longer and they change the temperature distribution. And the lower 2 figures tell you about the fraction, the horizontal average fraction that's solid. And for reasons that, again, I argue with my co-authors, but there are something like 5 of them and only one of me, and they've used phi up here and phi down where I'd use it the other way around. But what you see, that there's quite a significant change, and quite a rapid change. Well, rapid in the sense that it can change quite quickly at the beginning, but then these experiments go on for something like 2 days or so, and that's a longer change. Now, I don't want to go into detail in the mathematics, because that would take me a whole lecture course rather than just one seminar. Let me just say that we have done some mathematics, and these are the mathematical equations in the different stages, because there are different important principles, as I've already outlined, in the different stages, and you get some idea of the comparison and agreement between the theory and the experiment. This is now what it looks like. This is showing you the brine and porous ice, and you see when it freezes from above, so there's downward freezing, then you get these large brine columns where they're interacting, with the ice, and then in the lower line, in B in other words, it's when you have upward freezing. In other words, it's colder at the bottom, and you see these ice, but with brine layers going up. This is now a movie to show you what goes on, and you can see it's incredibly speeded up. I haven't been talking for 20 hours, I guarantee you. And here it is showing you again, just so that you see. This is now the cooling from above, and you see -9 at the top, 0 at the bottom. And so, of course, as I showed you in the diagram right at the beginning, there's a temperature which no solid will form because of the increase in salinity. But you see the structure here is quite remarkable. And this now looks basically at the structure at different times. So time is along the horizontal axis, and everything that's blue is downward freezing. In other words, it's colder at the top, and red is upward freezing. And you see, and this I found most surprising, that there's not a lot of difference. There's a greater difference on the strength of the brine solution. So at the top on the left-hand one, it's 1/3 of a mole of salt. Then we have 0.6 of a mole, so double that, and then double that again, 1.2 moles. So there's not an enormous difference due to the salinity content, and not as big a difference in how it's done. And so you see all of them here again. Oh, this just shows more or less the same thing again, but it shows it all together. And I think the details are not shown until a later slide. This is now our numerical calculations, basically of the force on the system that's forcing it to solidify, and our theory shows that the viscosity that you have doesn't really make much of a difference, and the viscosity of course changes with the salt content, but in our calculations it just changes the viscosity. Here again is indication of how things change with time, how either on downward or upward freezing as a function of time, the structure will change. And the salt diffuses, double diffusion plays a large role, because the temperature diffuses much more rapidly, like 100 times more rapidly than the salt. And this is now the vertical position of the brine pockets over time, and on the left-hand side for downward freezing, and upward side for upward freezing. And in some sense, the remarkable thing is that how similar they are. The brine pockets change more or less the same way. Our theory is indicated by the dashed lines, and our experiments, and we did lots of experiments with the same conditions, and there were slight differences are shown by the rectangles. And you see there's not bad agreement, so that's quite good. This is now, again, the motion is a function of time, initialized so that it falls together as best it can. And here is looking at it really much more deeply, and I hope you can see it big on the slide, better than I can see it, where the one is the brine columns, which you see, and 2 are the stripes, and 3 is virtually pure ice. It's virtually pure A, as I showed you on the phase diagram, and B, if you like, because it's cooled from the top. And you see that exactly where you are does make a little bit of difference, but what makes a much bigger difference is from top to bottom, even though that's 1 centimetre, and you see that really does make a difference, and it changes with time. Well, here are the rates, and again, this is really showing you the same sort of slide and equations that we use. It's basically conservation of salt, conservation of fluid, thermal variations. It's quite a complicated business. And this is just another slide of some of the details. I don't think we need to go through that. But as is known, it takes a long time to freeze salt from, or freeze ice rather, from a salty solution, and this indicates it. So, what I'd like to do is to give you some take-home messages. First of all, I've said brine freezing can be roughly divided into 3 stages. The first stage, which happens very rapidly, starts from nucleation to some sort of local equilibrium, but not global, and it happens independent of the long-range heat and mass transfer. Then we go into a second stage, S2, where there's a rough global equilibrium. The diffusion of the temperature is much more rapid than that of the salt. There can be mass transfer due to the brine extrusion as the ice forms, but some of the brine is kept in the ice, and that's important. And then there's the question of volume expansion of the ice, and convection plays a very large role. Then we have diffusion gradually coming in when the temperature has more or less done its role, but that's a slow mechanism, and the residual brine stays trapped in the porous end because in the porous end, ice rather, because that it can't get out. Now, some more take-home messages, and that's the end. You get these random, of course, stripe patterns. We did some experiments a number of times with exactly the same conditions, and what it looked like each time was different. No doubt depends on maybe little impurities. Is the water totally pure? Maybe even on little motions, minute motions in the experiment taking place. I mean, a train 1 mile away can shake the earth and do things. But they play a role, and the patterns do change with time. This now just says the difference between the columns and the skirts, and they definitely occur right at the beginning, but right at the beginning means in our experimental tank a day or so in the real conditions, and no doubt a month or so. And you have a porous medium with a nanoscale attitude that keeps some of the brine there, and that's of course important. Now, the people I worked with are shown here. Liang Li, professor at Westlake University, and two of these guys, I've just forgotten which, graduate students, two are postdocs, and we luckily had this, well, no, not luckily, we had this accepted by JFM just a month ago, but it hasn't yet actually appeared in print. But this is the title of the paper, Microscopic Salt Extrusion Dynamics, bidirectional freezing in brine. As I said, it was accepted on the 22nd of August, so it's almost a month away.